Hello everyone, welcome to the next lecture in the Neural Networks from Scratch series. So, first, let me recap whatever we have done so far. Up till now, what we have done is that we have coded the class layer dense, which essentially looks something like this. And we saw this in the last lecture where we had two methods, the init method, which initializes the weights, and then a method called forward, which basically takes a dot product between the inputs and the weights and adds the biases, and it gives the output to a layer. We saw that this is tremendously useful in having multiple layers. So even if we have multiple layers, we can just call this layer dense class every time we want to initialize a new layer. So then we don't need to write this dot product every single time when we define a new layer. So then what we can do simply is that if you define the first layer as layer dense 2 3, which has been defined here like this, and dense 1 dot forward comma and x, which is the input, this is the output of the first layer. Then if you can directly define the second layer, dense 2 is layer dense, and the number of inputs will be the number of outputs of the previous layer, right? And that will be 3, and the number of neurons can be anything. So let's say if these are 10 neurons, this is the second layer which I have created. Then the output of the second layer would be dense 2 dot forward, um, dense 1 dot forward of x. That's it. This will be the output of the second layer. So this is how you chain multiple layers together using the layer dense class in Python. And we looked at this last time. Um, so let me just zoom out a bit. Okay. And we saw that this works for a batch of data as well. So the first row is the output of the three neurons for the first batch of data. The second row is the output of the three neurons for the second batch of data. And the fifth row is the output of the three neurons for the fifth batch of data. We also saw that throughout this rest of the course, we are going to be dealing with this spiral data, which has two input dimensions, the x1 and x2. And we are going to be performing a classification task as we move forward. So the data has been encoded so that it's in three categories: red, green, and blue. You can see that each of the class represents a different spiral. The red spiral is here, the green spiral is here, and the blue spiral is here. Eventually, we will code the neural network so that it will be able to distinguish between these three colors. So we have reached a stage where we can stack number of layers together using the layer dense class. But up till now, there is one very important feature of neural networks which I have not yet introduced, and that is called as activation functions. So let me switch to the writing functionality here. Activation functions. Now, what are activation functions and why are they needed in neural networks? So, in the machine learning teach by doing project, which is another playlist which I have a 1 hour lecture on explaining activation functions in detail, all of them. And I'm going to be linking them in this video. I'm going to be linking that video. So you can just click on that video to see more details about activation functions. In this video, I'm just going to give you a brief introduction of what are activation functions and why do we really need them in the first place. So essentially, uh, the reason we need activation functions is to implement non-linearities. So let me explain what that means. So up till now, we have looked at neural network architecture, which looks something like this. There are four inputs and there are three neurons, and then every neuron has an output, which is then fed into the next layer, and that output looks something like x into w plus b. Now, what activation function says that this is not good. We need to add a more non-linearities. Up till now, everything is linear, and so we are not essentially making the neural network powerful. So what activation function say is that instead of feeding this output directly into the next layer, we pass it through another layer which is called as an activation layer. So there is an activation layer in between, and the when these outputs pass through the activation layer, what simply happens is a function f gets applied. So then it's f of x into w plus b, and this is then fed into the next layer. So instead of directly feeding this x into w plus b into the next layer, we apply a function and then it is fed into the next layer. The reason this function is applied is that this function typically introduces non-linearities, and I'll explain in a moment what that means. But this activation function really gives the power to the neural networks to be expressive, to be able to capture any underlying function. So when you think of the neural network now, you can think of it as a block representation. There is an input x which goes into a set of weight matrices initially of the first hidden layer. Then the output is x into w plus b. Then it goes into an activation layer a1. The output of this is f of x into w plus b. And then we go to the second layer again. So then there is w2, then there is a2 dot 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 wn and an, and then we have the output of this neural network. So remember that an activation layer really needs to be added at every hidden layer and even at the output layer when we do the forward pass. Okay, and the reason an activation function is needed is because if you don't have the activation function, let's say that everything is just linear, let's see what happens. Okay, so look at the blue curve here. The blue curve is my underlying data and I want to capture it. Okay, now imagine that we don't have an activation function or we just have a linear activation. So let's say these blocks here, a1 a2 dot 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 an, are just y equal to x. If these blocks are just y equal to x, it means that the f is just an identity function. So it's effectively like not having these activation functions, right? So if we don't have an activation function, or if we have an identity activation like a linear activation function y equal to x, and let's say we train a neural network with two hidden layers and eight neurons in each layer on this underlying blue data, the result which we obtain is this pink line, and you can see that it's just a linear function. And the reason it's linear is because look at this block representation. If we don't, if this activation function is just an identity function, there is no non-linearity here, right? The output from the first weights is x into w plus b, that is linear. When it passes through y equal to x, this will again be x into w plus b. Then the second weight matrix will again apply a linear transformation. So essentially all we will have is straight lines which are the outputs of the neural network. And that's why we won't be able to capture this complicated function such as the sine function in this case. This is the reason activation functions exist. We need to have some non-linearity in this neural network, and the advantage of activation functions is that when you add these non-linear functions and when you stack them on top of each other, the non-linearity compounds, due to which we can approximate more and more and more complex functions. We don't want this pink line here, it's just a linear function. We would have just done regression in this case. But a neural network is much more powerful, and the real power comes from these activation functions. So, what are activation functions and what do they represent? So, it turns out that one of the most famous activation functions is something called ReLU, or rectified linear unit, and it just differs from the linear function in one small simple way. For x positive, it is y equal to x, but if x is negative, the output is 0. And this is the ReLU activation function. Uh, can you think of why the ReLU activation function is so powerful? Why do we even make this small change, such as putting everything on the negative side to 0? How does that help us? How does that help us capture complicated functions? So let me give you a small demonstration here, okay? Let's say um, I have a function which is, this is the neuron 1 and this is neuron 2 and this is my output, okay? So these are the inputs from the first neuron to the second neuron. These are the inputs from the first neuron I1, inputs from the second neuron I2, and then the output is I1 plus I2. Okay. And the underlying function which I want to capture using this simple neural network is something like this. So this is not a straight line, but it's a non-linear function which looks like a triangle. Now, if I don't have an activation function, then I1 will probably just be a linear function of x, right? So if no activation, then I1 will be a linear function of x, and I2 will also be a linear function. And whatever the slopes, even if we add I1 and I2, the output will just be a linear function. So we will never be able to capture this triangular shape like this. So this is the case when we have no activation function or the identity activation function. But now let's say if we have the ReLU, okay, uh, and the I1 is just a simple ReLU. So I'm going to say that I1 is just ReLU of X, which will look like this. Okay, and now what I'm going to say is that uh, I'm going to play around a bit with I2. So first, I want you to check what is ReLU of x minus 0 point or x minus 2. So if ReLU of x looks like this, ReLU of x minus 2 will be max of 0 comma x minus 2, right? So at x equal to 2, it will have this break off point or transition point. So this will look something like this, correct? Now, what if I have negative of ReLU? What if I have negative of ReLU x minus 2? What will happen to this function now is that it will flip because I am taking a negative. So it will be something like this. Okay. And then what if I add 2 to this? So what will be 2 minus ReLU of x minus 2? It will look uh, something like this. Something like this. Now, what if, so let's say I2 is this. What if I add I1 and I2 now? So if you add I1 and I2, what you will get is that the resultant function will kind of have like a positive thing here, because this is anyway 0 on the negative side. Then it will raise everything here by this much value, and then it will have this downward slope. It will have something like this. Now, do you see how close we are to capturing this triangle? Uh, this is where we are at right now. And I could just even add one simple neuron to bring this side down so that we just have a triangle. That is the beauty of the ReLU function. Just making sure that one side is 0 introduces a non-linearity. And so we can stack multiple ReLUs together by offsetting them like this, by changing their slope, etc. And we can capture even complex shapes. We can even capture sinusoidal functions like this. That's why it's so important to have non-linearities in the activation function and not just have it linear. So it turns out that if you use the ReLU activation function with two hidden layers and eight neurons, you can perfectly capture this underlying sine function. In fact, there is a very nice animation to show how the ReLU actually can be trained to capture the sine function, and I'm just displaying it on the screen right now. So here we are just showing how you can adjust the slope of the ReLU function by playing around with the offset and by playing around with how much you add or subtract to it. Now slowly we'll be going to the point where we'll be approximating the sine function. Okay, so look at this right now. So currently we only have two neurons and we are adjusting the weights, and the red line is what we have from the ReLU function right now, and the green line is the underlying data which we wish to approximate. So you can see here we are playing around with the input uh, to the second neuron, which we are going to pass it to the ReLU, and here we are playing with the input of the last neuron, and now we bring the second neurons into the picture and we change their input, we change their bias, and here you can see how using the non-linearities in the ReLU function we are slowly trying to approximate the underlying green curve, which is the sine function. So two neurons are done. Now we bring a neuron again at the bottom and we change its input to offset the red curve. Now we bring the third set of neurons in the picture. So now you can see that we are slowly trying to capture this part of the sine curve. We have captured up till the peak and now we are capturing the decline. And towards the end of this video you will see that we can adjust the slope of the ReLU and the shoot off point, and then we can capture any underlying function which we need. Here I'm just showing you how we can change the offset term and the slope of the ReLU to capture the sine function. Okay, so this was a brief demonstration to show why we need to introduce non-linearities in our activation function and how that helps in neural networks. Now I just want to show you how to implement the ReLU class in code. So here you can see the ReLU is just a maximum of 0 comma x, right? So in numpy that just written as np dot max of 0 comma x. So here you can see if we have an input, sorry, in numpy it's written np dot maximum 0 comma x. So let me just make that change over here. In numpy it's written np dot maximum 0 comma x. So if you have an input array right like this, and if you define the output as np dot maximum 0 comma inputs, it will essentially trim off all the inputs which are negative, put them to 0 like this, and then all the positive values will be retained. We can implement it as a class very simply, similar to the way we did using the layer dense class. So here is a class which is called activation underscore ReLU, and we don't need to initialize anything here. Similar, unlike what we did in the layer dense, we just need to define a forward pass or a forward method which takes in the inputs and then applies the ReLU. That's it. So what this forward function is doing is that it takes in these inputs, which are the outputs from the neurons, and then it just applies the ReLU function to create the output, which will be fed into the next layer. So the forward method just takes inputs as an attribute, and then it does np dot maximum 0 comma inputs, and then it outputs the result. So then the output will have the same shape as inputs. So this is the simple implementation of the ReLU activation class in Python. Remember, the data set which we are dealing with involves us to do a classification task. So we are given a data set and we need to classify it into three types. ReLU is not the best activation function really to be used for classification tasks. Uh, in classification, we really want an activation function which can tell us which class the data belongs to. So let's say if we have a neural network block representation which looks something like this. uh, Let me draw it again. Let's say if we have a neural network block representation which looks something like this is A1, then W2, A2, and let's say this is my final layer which is W, let's say 100 and A100, and this is my output. Okay. So essentially, these layers can be ReLU. This can be a ReLU layer. This can be a ReLU activation layer. But the final activation function cannot be ReLU, because in the final activation layer, I need a prediction as to what my class really belongs to, right? So let's say I have input from this spiral data, and as I told you, there are two dimensions to the input, x1 and x2. So let's say I have x1 and I have x2 as inputs, and let's say the first layer has three neurons. So these two inputs feed into these three neurons. Let's say the second layer also has three neurons. uh, let's say or let's say the second layer has two neurons, which is my final layer, right? So these two inputs will feed into the first layer. These these two will feed into the next layer, and then there will be an output from this neuron, and then there will be an output from this neuron. um, and maybe there should be one more neuron, because I have three color categories, right, in the spiral data. So I have outputs, okay, from three neurons. Maybe this is 5, maybe this is 10, and maybe this is 15. Based on these three outputs, I want to make a guess as to this input x1 and x2, which color does it belong to. Does it belong to the red class, does it belong to the green class, or does it belong to the blue class? This is a classification problem, right? So any new input, my main task is to train a neural network so that the output from the final neurons is such that it can tell me something about which class it belongs to. So based on this output, I want to make some prediction that whether this data x1 comma x2 it belongs to the red class, it belongs to the blue class, or it belongs to the green class. And if we have a ReLU activation function at the end, we may get outputs like these. There are two problems with these outputs. First of all, they are on a scale of all real numbers. So they can be 0, 100, 1000, they can be anything. And that does not tell me anything too much about whether I can just see that, oh, this magnitude is higher. So maybe the green class is higher. Maybe. This 5 magnitude is the lowest. So maybe the red class is the lowest. So that's the first problem. The second problem is that there is no way these outputs are related to probabilities. Ideally, I want outputs which can tell me what is the probability that my input is in red class, what is the probability that the input is in blue class, and what is the probability that the input is in green class, right? So essentially, what actually I want to do is that I want all these outputs to sum to one, but these are not summing to anything. And that actually leads us to another activation function which is called as the softmax activation function. And so all other blocks can be ReLU, but towards the end, just before we have the output, we need the softmax activation function. This is usually the most preferred activation function for a multi-class classification like what we have. This function does two things. It makes sure that the output is 0 to 1, it lies between 0 to 1, and it makes sure that the output is related to probabilities. So all of the outputs essentially sum to 1. So just by taking a single glance, we can say uh, which class is the most probable. So what is the softmax activation function? Let me explain it to you in a very simple manner. So let's say these are the outputs. O1 is equal to 5, O2 is equal to 10, and O3 is equal to 15. What softmax does is that it makes a transformation. It first takes the exponential of this value, e raised to 5, and then divides it by e raised to 5 plus e raised to 10 plus e raised to 15. So this will be now the output from the first neuron. The output from the second neuron will be e raised to 10 divided by e raised to 5 plus e raised to 10 plus e raised to 15. And the output from the third neuron will be e raised to 15 divided by e raised to 5 plus e raised to 10 plus e raised to 15. So first thing which you need to check is that since we are doing exponent, all of these quantities will be positive. That's number one. Second thing to check is that in all these quantities, if you see, the denominator is always greater than the numerator. Because in the denominator, we are taking a summation and the numerator is just one term of that summation. So they lie between 0 and 1. And this is also a tick. And secondly, the most important, if you sum these three, the sum will be e raised to 5 plus e raised to 10 plus e raised to 15 divided by e raised to 5 plus e raised to 10 plus e raised to 15. So the sum is equal to 1. So now these will be related more to probabilities. I can just look at the output and say that the probability of my output being in the green class is e raised to 15 divided by e raised to 5 plus e raised to 10 plus e raised to 15, let's say. So this is the softmax activation function. And now we need to have an understanding of how this needs to be implemented really in code. Okay. So remember that this is the neural network which we are considering, right? But the input is usually a batch of data which looks something like this. This is the first batch, this is the second batch, third batch, dot dot dot. So maybe we'll have 100 batches of data like this. 100. So the number of rows can be 100 and the number of columns will be 2 because the input data dimension is 2. So if we have 3 neurons as output, the output will be 1, 2, 3 for each data, and there will be 100 like these. There will be 100. So now let us look at what we need to do with this output. So let's say we have an output which looks something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say this is the output for 3 batches of data. This is the first batch, this is the second batch, and this is the third batch. Now this actually needs to be replaced with e. So in the first batch, we will need to take a exponent of all these values and divide by the summation. So the first will be e raised to 1 by e raised to 1 plus e raised to 2 plus e raised to 3. The second will be e raised to 2 by e raised to 1 plus e raised to 2 plus e raised to 3. And the third will be e raised to 3 divided by e raised to 1 plus e raised to 2 plus e raised to 3. This will be the updated first row. Similarly, the updated second row will be e raised to 4 by e raised to 4 plus e raised to 5 plus e raised to 6 dot dot dot. And the updated third row will be e raised to 7 by e raised to 7 plus e raised to 8 plus e raised to 9 and dot dot dot. Okay. So this is actually what we want to do. So we want to take an exponent of all these values and just divide it by the row summation of these exponents. Uh, Before we actually do that, in practical settings, we are going to do one more thing. From every row, we are going to subtract the maximum value of that row before we take an exponent. And the reason for this is to prevent the exponent values from becoming very large. So that is just one small practical addition which we will be doing. Now I am going to take you to the code in Python to see how the softmax activation class is implemented. I hope you have understood up till this point. And when we go to the code, remember that what we learned in the previous lecture of axis equal to 1, axis equal to 0 sums along the rows, axis equal to 1 sums along the columns. And we also learned that it's very important to use keep dims equal to true because that retains the dimensions when we do summation along axis. Okay. So if you have not seen this lecture, I am going to link it above. It's very important for you to see this before you understand how the Softmax activation class is really implemented. So let us jump into the code. So we saw the activation function for ReLU. Now let us see how the activation function for Softmax is implemented. Before that, let's say we have these inputs. The first row is 1, 2, 3. So let me actually write this here so that I want you to understand everything from scratch. So I won't skip any step. So the input which we are looking here is 1, 2, 3, 2.5. 1, 2, 3, 2.5. Then 2, 5 minus 1, 2. 2, 5 minus 1, 2. And then minus 1.5, 2.7, 3.3, and minus zero point 0.8. Minus 1.5, 2.7, 3.3, and minus zero point 0.8. Okay. Now, the first thing which we need to do is subtract the maximum value from each row from that row. Okay. So here, look at this. The reason why we are doing x is equal to 1 is that we want to take a maximum value of the first row and then subtract it from all the elements of the first row. If we did x is equal to 0 here, it would take the maximum value from the first column. That's why we are taking x is equal to 1. And the reason we use keep dims equal to true is because uh, the broadcasting needs to be correct. So for example, when you do the np, so when you do the np dot max, this matrix A, let's say, comma x is equal to 1, if you use keep dims equal to true, you will get a column vector which looks like this: 2.5, 5, and 3.3, which are the maximum values from each row. And then you need to do this subtraction, right? So what Python will do internally is that it will use broadcasting. So it will copy these values two times so that the matrix dimensions are aligned. So what it will do is that it will copy these values actually three times so that you can do this subtraction. So when you subtract from the first row, 2.5 will be subtracted from every element. From the second row, 5 will be subtracted from every element. And from the third row, 3.3 will be subtracted from every element. If you don't use keep dims equal to true, you will land into trouble, because what you will end up doing is that you will end up uh, subtracting 2.5, 5, 3.3, etc. from the first row. So this will be a huge mess. I deliberately have the previous lecture on broadcasting so that you understand this, and I'm linking it above again for reference, where I've taken an exact same example and I've explained to you why we need to use keep dims equal to true. So this is the first step. Subtract the maximum value from each row from the inputs, and then you take the exponent. So up till now, what we have essentially done is that we have taken the exponents, and now we have to divide by the summation of each row, right? So then what we do is we take these exponentiated values and we use the np dot sum operation, and again keep x is equal to 1 and keep dims equal to true. So let me show you why. So again, take a look at this particular thing. Up till now, let's look at the first row. Up till now, we have e raised to 1, e raised to 2, and e raised to 3. But now we need to divide every element by the summation. So what we do is that, let me write this matrix fully: e raised to 4, e raised to 5, e raised to 6, e raised to 7, e raised to 8, e raised to 9. Now, if you take this matrix and you do np dot sum this matrix x is equal to 1 and keep dims equal to true. So np dot sum, let's say this matrix is called b comma x is equal to 1 and keep dims equal to true. Remember, x is equal to 1 sums the columns, right? So you will get a matrix which looks like a column matrix: e raised to 1 plus e raised to 2 plus e raised to 3 e raised to 4 plus e raised to 5 plus e raised to 6, and e raised to 7 plus e raised to 8 plus e raised to 9. Let's say this is matrix C. And now you're doing the division operation between B and C. See, you're dividing the original matrix B with this C. So you're doing the division operation now, B divided by C. What Python will do is that it will now replicate this two times, so that now the C matrix will be made sure to have same dimensions as B in the broadcasting rule. So then it will just be e raised to 1 plus e raised to 2 plus e raised to 3, e raised to 1 plus e raised to 2 plus e raised to 3, e raised to 1 plus e raised to 2 plus e raised to 3, e raised to 4 plus e raised to 5 plus e raised to 6 two times, e raised to 7 plus e raised to 8 plus e raised to 9 two times. And then when we divide b with this, you can now do element wise division. So then the result will be that the first element of this will be divided with the first element of this, the second element of this will be divided with the second element, etc. Then we will get exactly this value which we needed. And if you do not use keep dims equal to true, you will get a wrong answer here, and I really encourage you to try this on your own. The reason we had the previous lecture is only so that you can understand these two commands when we write the softmax. Okay, so in the first command here, we subtract the maximum value of each row, and in the second command here, we just take the division of this exponent matrix with the summation of the exponent, and then broadcasting rules are used. So ultimately, we get a matrix like this where every output is converted into probabilities. Now you can actually print these probabilities and take the summation. So here is the output matrix from this input matrix. Look at the first row. The first row of this output matrix uh, corresponds to the first batch and the probabilities. And if you sum it up, it will sum to 1. The second row corresponds to the second batch, and if you sum it up, it will sum up to 1. Third row corresponds to the third batch, and if you sum it up, it will sum up to 1. Uh, okay, so this is how essentially the softmax activation function is employed. Now let us construct the softmax activation class. So here we have a forward function, and what it does is it takes an in forward method rather. It takes an input, subtracts the maximum value, and then from the exponentiated values, it just divides it by the sum of the exponent values. So in this class, actually exactly the same things are written as has been written above. So this is how the softmax activation function is actually implemented in practice. Okay. Now I want to show you how these things all align together for our spiral data. So how we can use the different classes which we have created and create an output. So in this code which I'm going to show you now, what is simply done is that we have an input data which are two values. It goes through, I think initially it goes through three neurons. So initially it goes through a layer of three neurons, then it goes through a layer of three neurons, and then there is an output. Okay. But in terms of activations, here the ReLU activation function is used, and here the softmax activation function is used. So to create this layer, we will use the layer dense class. Then we will use the ReLU class to apply the activation function. Then we will again use layer dense class to create the second layer. And then we will use the softmax to apply this activation function to the output of this second layer. And let's see how easy it is to do that. So first we have the data set of 100 data points. Now we create the first layer with two inputs and three neurons. we initiate the first activation. Remember, no attribute needs to be passed because there is no initialization function in this class. Then we create the second layer with three inputs and three neurons, exactly like what we saw here. And then we initiate an instance of the softmax activation. Now let us start doing the forward pass. So dense one dot forward, what this will do is that it will generate outputs from the first layer of neurons, wx plus b, wx plus b. Then this output of the first layer, which is dense one dot output, it will be passed to the first activation. So then this will be passed to the ReLU, wx plus b. And then the output of this will be passed as an input to the second layer. So then this is the output of the first layer, activation one dot forward, dense one dot output. Now when you do the dense two dot forward for the second layer, you use the output of the previous activation as this input. And then the dense 2 dot forward is this, so w2 into x plus b. This x is the input, which is this, which is the output from the first activation. And then finally you apply the softmax, which is activation 2 dot forward. That's it, it's as simple as that. So essentially what you get finally is that for all the 100 data samples you have three outputs. So this is 100 data samples and you have since we have three output neurons. And what I'm doing here is that I'm plotting the first five. Now just look at the each row, it will sum up to 1 because every element now corresponds to the probability. So the first element is, when we look at the first batch of input, probability of being red, probability of being green, and probability of being blue, and that is similar to all the rows. Okay, so now you can see how defining classes makes it very easy to execute the entire forward pass what we have done in these 10 to 11 lines of code. For that, you just need to understand the first layer, then the ReLU, then second layer, then softmax. That's it. And in 11 lines of code, you can execute this forward pass. So this was a bit of a dense lecture and it also depended a bit on the previous lecture, but I deliberately created the previous lecture on broadcasting so that you will understand this. So please stick with me through this course because now things are getting interesting. After this lecture, we'll move to the loss function and then we'll move to back propagation after that. So thank you so much, everyone. I know things are getting a bit complex, but stick with me and try to replicate this in the code so that you understand exactly what is going on. As always, I try to explain everything from scratch. That's why lectures become a bit long, but I think it's needed. So thank you, everyone, and I'll see you in the next lecture.